The random variable x follows normal distribution, that is x follows n of sigma nu comma sigma square, and p of 9.6 less than x less than or equal to 13.8 is given as 0.7008, and p of x greater than 9.6 is given as 0.8159. Given sigma is equal to 2, sigma phi of 0.9 is equal to 0.8159, and phi of 1.2 is given as 0.8849. We have to find the value of mu. P of 9.6 less than or equal to x less than or equal to 13.8 is equal to P of x less than or equal to 13.8 minus P of x less than or equal to 9.6. So P of x less than or equal to, this is equal to phi of 13.8 minus mu by 2 minus phi of 9.6 minus mu by 2. So here, and P of x greater than 9.6 is equal to 1 minus P of x less than or equal to 9.6 is equal to 1 minus phi of 9.6 minus mu by 2. And if we solve this one, phi of 13.8 minus mu by 2 minus phi of 9.6 minus mu by 2 is equal to 0.7008, implies phi of 13.8 minus mu by 2 is equal to 0.7008 plus 1 minus 0.8159. Implies phi of 13.8 minus mu by 2 is equal to 0.8849 is equal to phi of 1.2, implies 13.8 minus mu by 2 is equal to 1.2. So we'll be getting mu as 11.4. So here option C is the correct one. Trapezoidal rule of integration gives exact result in the function being integrated is, if the function being integrated is first one constant, second one linear, third one quadratic, and fourth one cubic. Here the correct answer is both constant and linear, but not quadratic and cubic. Why? Because while if we use trapezoidal rule, the area under curves will not be considered in trapezoidal rule. The behavior at both just starting and ending is considered, but not it will not consider area under curves. So here quadratic and cubic. So here correct answer is both constant and linear, but not quadratic and cubic. So here correct option is option B. Consider the following graph. A graph is given. The question is the vertex connectivity and edge connectivity of the given graph are respectively. Here one graph is given and we have to find the vertex connectivity and edge connectivity of the given graph. In order to solve this problem, first of all we need to know what is vertex connectivity and what is edge connectivity. Vertex connectivity is nothing but minimum number of vertices whose deletion from the graph disconnects the graph. This is the minimum number of vertices whose deletion from the graph from the graph disconnects the graph. This is the definition for vertex connectivity. So if we see the given graph here, the minimum number of vertices in order to make the minimum number of vertices should be deleted in order to make the graph disconnects is 1. If we delete this vertex, we can see that the graph would be disconnected into two components. So here the vertex connectivity is 1. Vertex connectivity is 1. Now we have to find edge connectivity. Let us write the definition for edge connectivity. Edge connectivity is similar to vertex connectivity. Edge connectivity means the minimum number of edges whose deletion from the graph disconnects it. This is also called as line connectivity. Edge connectivity is also called as line connectivity, which is minimum number of edges whose deletion from the graph disconnects it. So if you see the given graph here, we can say that the minimum number of edges which should be deleted in order to make the graph disconnected is 3. So let us if we take here, we have to delete these 3 edges in order to separate this vertex. For this vertex also we need to remove 3 edges, 1, 2 and 3. So, here let us suppose if we want to delete this one, separate this one, here we have to delete 1, 2, 3 and 4. So here like this, if we find the edge connectivity, we will be getting minimum 3 edges should be deleted to make the graph disconnected. So here edge connectivity is 3 and vertex connectivity is 1, which is option D.